So I'm going to continue with what I finished last time, yesterday, which is the description of the perturbations from inflation. Yeah, thank you very much. Those fluctuations are both scalar and tensor, as I described. In the scalar part, there are actually two components. There is the scalar field, which acts like the inflaton, and then there are scalar metric fluctuations. We know within the theory of gauge invariant metric fluctuations, there are actually 10 degrees of freedom. Out of those, 4 scalars, 4 vectors, and 2 tensors. The 4 scalars actually cannot all be gauge invariant. There's clearly a gauge transformation or coordinate transformation that we can do that will relate the different scalar components. So there's a choice, a specific choice, which is the one I have taken here. It's called the conformal Newtonian gauge. It's an election of coordinates in such a way that the 4 different scalar components can be written as just 2 components. The one that goes with the stereo component of the metric, and one that goes with the ij component of the metric. So one would be the Newtonian potential, and the other would be the usual curvature perturbation. However, in the context of inflation, where the stress energy momentum tensor is symmetric, there is no anisotropy, then there's another constraint which tells you that the Newtonian potential and the curvature should be equal. Okay? Phi equals psi. And this is the reason why the curvature fluctuation, which is related to phi, has exactly the same amplitude as the Newtonian potential. So we only have one scalar metric fluctuation. Okay? This is very specific to inflation. There will be, of course, a tensor component, transverse traceless component in this Newtonian gauge. This is a gravitational wave. It's propagating at the speed of gravitational waves. Remember that photons travel at the speed of gravity, and not the other way around. So the Newtonian potential is going to mix with the scalar fluctuation of the inflaton in such a way, like Mohanov realized, that it has a second order action that one can use to quantize this fluctuation. So it's not true that the scalar metric fluctuation and the scalar fluctuation from the inflaton act independently. No, they are tied up. They are linked together. And it's the common variable u, the Mohanov variable, which satisfies the second order equation and which can be quantized. And indeed, one can describe with creation and manipulation operators, as I was describing yesterday, a Fock space for this field, this combined field, which satisfies computation relations, equal time computation relations, and can be used to quantize the field and find its mode equation. Something which is very peculiar of inflation and will not happen when fluctuations will re-enter again and will go through gravitational collapse, is that at least during inflation, you can treat this quantum field, in general it's a quantum field theory, you can treat it as an infinite harmonic oscillator quantum mechanics. So you can treat each one of those modes, since their amplitude is small, and the mode-mode coupling is suppressed to much higher order. That means that you can treat all this as a free field. Okay? And therefore, from quantum field theory, you recover infinite harmonic quantum mechanics. So one can treat each one of these modes with its mode equation as an independent mode, which, as we will see, go out of the horizon, back into the horizon at a given time, given by its wave number. But this equation, which is really like a Schrödinger-like equation, can be resolved. And again, remember what I was saying yesterday, there's a time-dependent potential. This time dependence will induce growth of the amplitude of the fluctuation. That's the thing which makes these so special. So really, this is not quantum field theory as we're used to in flat space-time. It's quantum field theory in a curved pattern. This time, it's time curvature which is determining the rapid growth of the mode. Okay. Right, so remember Schrödinger-like, these are spatial derivatives, here they are time derivatives. Right, so how do we solve this? Well, if we use the Stallman parameters that we were describing just in the previous lecture, There's something quite interesting. If we evaluate the evolution of those lower order parameters, we see that they are second order in their evolution. That means that if these are tiny objects, tiny quantities, then they're essentially constant. It's a consequence of them being small. Okay? Now, if they are a constant, then it's extremely easy to find what is the potential for those modes. Remember, this was the time-dependent potential. Because it's actually 1 over the conformal time squared times a quantity which is constant and depends on this lower order parameter. And this will play a role, as you will see. This is going to determine not just the amplitude of the fluctuation when it leaves the horizon, it's going to depend on also how much that amplitude changes as a function of time through the evolution, slow evolution of epsilon and delta. That is going to determine the spectral indices, how much the amplitude changes as a function of wavelengths. Okay, so there are exact solutions that one can work out. It's clear that for modes that have wavelengths much smaller than the size of the horizon, that is, we're deep inside the horizon during inflation. The horizon is a de Sitter horizon, it's essentially fixed. So if we look for wavelengths which are well within the horizon, essentially through Riemann's theorem, you know that this curved space-time, which is that of de Sitter, asymptotically at a very small distance, is essentially Minkowski. You can always find a patch which is tangent to de Sitter. Okay? And this patch is Minkowski. So in Minkowski, we know what the fluctuations are. We know how to quantize them. We can use the Wronskian, which I think it was in the previous equation here. We can use the Wronskian for the normalization condition of these modes. And therefore, we can write those modes as the usual plane waves. So they're plane waves in Minkowski. So this is your initial condition. Think of quantum mechanics, here in this case, as a scattering problem. So we go to -infinity, we fix our Fock space, we know exactly what are the number of particles, we start in the vacuum, and we let those waves travel through a potential, which is time dependent. And we ask, what is the final wave as it has traversed through the interaction? And the final wave has very interesting property, you see from this equation here, that when you have very long wavelengths, much bigger than the horizon, k squared is essentially negligible compared to the potential. In that case, you see that there's an exact solution, which is uk proportional to z. And this is the mode solution on very large scale, not the cross. So this solution for k much smaller than h, superhorizon fluctuations, we should have an initial condition, which is plane waves, which ends up being essentially proportional to z. Okay? And the only dependence on the wave number will come on a coefficient which is constant, as a function of time. Right, so what are those solutions? Well, fortunately, that is a very simple equation, at least if the potential is of this type, and one can solve exactly for epsilon and delta sufficiently constant. And this is the exact solution, which has asymptotically these two behaviors. It looks horrible, but it's not. It's a simple expression in terms of the Hankel function of the first kind. For instance, for Leo 3 halves, which will correspond to exactly 0, this would be the Hankel function. Nothing horrible, it's perfectly natural. In general, if epsilon and delta are not 0, and nu is not 3 halves, then you will have a dependence on those coefficients. So, what is the behavior of those modes when they cross the horizon? They go out of the horizon during inflation. Let's see what's the behavior when k equals to 0. Remember, this is when the u becomes essentially proportional to z. So, this is the shape of the function. In that limit is nothing but the function k over ah to this coefficient. So, notice that this is already telling you that on very large scales, when you're finishing inflation, all those modes that have been coming out will be essentially like the power. They go like the power of k, with an index which is constant. So not surprisingly, we are going to find that those fluctuations are giving rise to a power spectrum of fluctuation, we will see in a minute, in the next transparencies, which are going to determine the fluctuation that we're going to see on logical structures, CMB and LSS. Okay, there's a coefficient which is very close to 1, which is to come here. But there's something quite interesting. It's true that u is proportional to z times a constant, but the metric fluctuation, the Newtonian potential, is not constant. U may be constant. Remember, u was a d phi plus z, couple of phi. Z So phi can be obtained from that behavior, and it's this constant C1 that we were describing before, times the time-dependent quantity. Of course, remember, the equation that phi satisfied was a second-order differential equation. So it should have two modes. We'll have a growing mode and a decay mode. Okay? The decay mode very quickly will die away. So you will be left with a growing mode. And the growing mode is this one. Decaying with the scale factor, very quickly this goes away, same as this. So from you can determine through the equations both phi and delta phi. And we'll see that this is going to be the quantity that we will use in order to determine the amplitude of fluctuations in the CMB. Now, phi may be gauge invariant, but as you see, it's not constant. However, Bartley in 1980 realized that there is a combination of phi and its derivative, which indeed still remains constant outside the horizon. And we'll see how it connects with U. And this quantity is this one. Whatever the value of phi, if you differentiate with respect to conformal time and added the rate of expansion conformal time times phi and divide by this quantity altogether, it seems quite horrible, right? That quantity altogether is constant on superparticle scales. Actually, you can work it out in certain gauge. So if you take the gauge invariant curvature perturbation RC, this would be the quantity that in a certain type of surface, in density type of surfaces, would act as curvature, gauge invariant. Okay? This quantity, which is a gauge invariant quantity, which is constant on energy density type of surfaces, will have, with the corrected part, which goes like k squared over ah squared, and therefore it's a dominant when we have very long wavelengths, it's essentially this quantity. Which, if you realize, you expand the U quantity, remember the U variable of Mohanov was A delta phi plus Z times phi, and A delta phi you write in terms of phi, that's exactly this expression. So this theta, which is the gauge invariant curvature perturbation of local energy density of the surfaces, is nothing but the ratio of U over Z. But remember, that was the thing that was constant on very large scales. Okay? Indeed, we see that. If we evaluate the time derivative, we observe this thing goes away, and we observe that this thing, on very large scales, is constant. It behaves as constant. And this is crucial, because it's going to make us this mapping that we were discussing yesterday. It's going to tell us that whatever happens before inflation, at some epoch in which fluctuations were generated, will be correlated with what happens when that mode re-enters back into the horizon without any change in amplitude. So, thanks to this is only true, by the way, for adiabatic fluctuations. I won't go into the issues of curvature fluctuation, but for the moment, let's suppose that all fluctuations are adiabatic. You have a single field. Then, fluctuations that happen way inside the horizon will be stretched by the expansion and will come back in much later in our present universe and still retain the information that what happened during inflation because the amplitude of the fluctuation remained constant. If it weren't for this miracle, we would not have any clue of how to correlate what happens today to what happened in the past. That's crucial. Okay, so for adiabatic superpolarizing modes, we can make such a mapping. And this is where this connection of the geodesics that we were saying yesterday comes in. So, this is a picture. We have our potential being approximately 2 over eta squared in conformal time. This would be your potential. You have modes that are well inside the horizon, cross the horizon. They remain constant outside the horizon and re-enter back in the Matter era. Also, Matter era has a potential which goes like 2 over eta squared. You can work that out from the same. And that's those constant, so you have eta block over 8, and you know how the scale factor grows with conformal time in the matter, look at eta squared, solve that, and that gives exactly 2 over eta squared. So this is a symmetric potential. Okay? From inflation matter. Fluctuations which are entering the horizon, say, at recombination or after recombination, those fluctuations are of this type. Very small case, which were fluctuating inside the horizon, when outside the horizon remain constant, and then fluctuating back in when they re-enter. Okay. Notice this is really very much like a scattering problem in quantum mechanics. Okay? So we're asking, what happens in this period? Okay? So this is crucial in order to make the connection for any geodesic given a given wave number from deep inside the horizon during inflation to today, where we can observe what happens with those fluctuations. Now, once we have the constant, this curvature fluctuation, which is constant on superparticle scales, we will need to correlate this with the metric fluctuation, because that's the quantity, the physical quantity, which is going to determine, for instance, CMB and LSS. There is a connection between the metric fluctuation, it's going to redshift and blueshift photons out of those potential wells. Photons will travel, coming out of potential wells, will be redshifted because they come from the top of the potential well, will be blueshifted. So we're going to see differences in the CMB coming from photons on different amplitudes of fluctuation at different wavelengths. So we have to correlate this curvature fluctuation R with the metric fluctuation phi. And this is the expression we had before. Remember, this was C1, this was the constant, and it had a time-dependent quantity, which for radiation era and matter era can be worked out. That is, for a biological fluid, it's just simply a constant that relates R to phi. In radiation, it's 2/3, in matter, it's 3/5. So that's all we need. Okay? The only thing we need is inflation produces fluctuation, go out of the horizon, come back in. When the amplitude of the fluctuation re-enters the horizon, that starts the clock for fluctuations to start oscillating with an amplitude given by whatever it was during the inflation, with a constant factor. Okay? That's great. So let's see cartoons. So quantum fluctuations within the horizon, when they're tiny, that is mid-Koskian, they grow out and stretch because of this tremendous expansion of space-time. Wavelengths are redshifted much faster than the horizon, and then when they re-enter back in, they contain information of what happened early inside the horizon. Now there's something quite interesting. The fact that the amplitude is proportional to this quantity c, which only depends very slightly on these lower parameters, mostly on the amplitude of the fluctuation, means that since the rate of expansion is very approximately constant, and these fluctuations are proportional to this rate of expansion, then as time progresses, more and more modes with very similar amplitudes are coming out of the horizon. What does that mean? That means that when they re-enter, the fluctuations, which remember have constant amplitude through horizon crossing, from the first to second horizon crossing, will have amplitudes which are very similar to each other. That only means that your spectrum essentially is scale invariant. Whatever the wavelength of the fluctuation when it left was proportional to a quantity that did not vary that much during those few defaults, 10 or so defaults. Okay? So those fluctuations which have not had much of a change in the amplitude will give rise to a scale invariant spectrum. And this is a sort of thing similar to radiation. A scale invariant spectrum where I have added a very long wave fluctuation, on top of which another fluctuation with similar amplitude, on top of it another fluctuation with similar amplitude, and so on and so on and so on. So when those fluctuations re-enter and that add up, this is linear perturbation theory, we are adding up, there's the principle of superposition of waves acting on these fluctuations. That means that matter will live in a combination, in a linear combination of all those fluctuations with different wavelengths. That's called a power spectrum. Okay? This power spectrum will have same amplitudes with different wavelengths, but it will have something quite interesting to do. If you add up all those fluctuations, you'll see that this would be the behavior of the metric fluctuation and obviously through Einstein equations, density contrast, which will show that fluctuations which are very rare, like this one, will come from adding up fluctuations one on top of each other. So you are producing a distribution of fluctuations which will have a mean and it will have a dispersion. And dispersion is dictated by the amplitude. Now there's something that I have not described here, which is crucial also. That is that given that during inflation we are describing this quantum field like some harmonic oscillators, and given that we've had enough time during the evolution of the universe before the fluctuation left the horizon, those quantum fluctuations have dropped to the ground state. So what is the ground state of a harmonic oscillator? A Gaussian. That means that all the fluctuations that we are dealing with here, whatever their amplitude, are Gaussian fluctuations. From a statistical point of view, a Gaussian is very interesting. you could find it because of very large number of degrees of freedom, like in the central limit theory, or like in this case, because of its quantum origin. So if we measure our fluctuations in the CMB or in logical structure to be very Gaussian, we are having an insight of what was the mechanism that generated those fluctuations back in the origin of the universe. So if they came from the ground state of fluctuations evolving during inflation, then they should have a Gaussian statistics. And indeed, that has been observed by Planck and W. even before. Okay? Let me continue on. So this horizon crossing, of course, will happen at different times for different wavelengths. But this is where the mapping comes that I was describing here. So wavelengths that left the horizon earlier, more equals before the end of inflation, will come in later. Those that were earlier, closer to the end of inflation, will come earlier, and so on. Eventually, as I was describing, there is a one-to-one mapping. Okay? And there is no crossing of geodesics. Okay? Exactly those geodesics that left the horizon very early on will remain outside. There's a congruence of geodesics, will remain outside the horizon and re-enter back in, and do not mix until once they are entering the horizon, they will go through nonlinear gravitational graphs. Then they will mix. Okay? So it's crucial that there is such a mapping, because then we can do the inverse problem. We can ask, what do we observe today? What is the structure we observe? This would be baryonic oscillations creating, for instance, galaxies and so on. Okay? So we can ask, how do these fluctuations that we observe today correlate to what the fluctuations were at the beginning of the universe? If we could go further, we could see the events that left the horizon earlier towards minus infinity, we start to raise our hopes to be in contact with quantum gravity effects. For the moment, we're only looking at quantum field theory in curved space-time effects. But it might be, if we manage to touch very sensitively what is the behavior of those hopes when they left the horizon, some of those features could be left in our solar universe today. It's extremely difficult, but that depends very much on the scale of inflation. And that's something which we still do. Okay, so remember that this was our causal region. Okay, anything which is below the horizon will be amenable to big contact. Obviously, those fluctuations that we see today, which came from the region within the horizon, were in fact in causal contact. They had a homogeneous patches because inflation had acted for plenty of epochs before those fluctuations left the horizon, and therefore it contains information that we can trace back and explain why do we see such temperature fluctuations over a background which is essentially homogeneous. There's no difference in temperature because they actually were in contact. That's also the causality problem. Okay? Fine, so let's see how that works out again in my pictures where the universe is a ball, the horizon during inflation is a tiny patch on it, and let us assume I'm adding now a little fluctuation with an even wavelength. So as time progresses, those patches which were together now start separating, their wavelengths also grow very fast with the size of the ball of the universe. Eventually those quasars just stretch apart, they become disconnected, and more, wavelengths are coming out of the horizon. You notice the wavelength was inside the horizon, then it became outside the horizon. Okay, the wavelength is bigger than the size of the horizon. Remember, during inflation, the horizon is essentially constant. Okay, it's achievements. So the wavelength which is stretched exponentially, it's been driven out. Eventually, after inflation, let's concentrate now on a single horizon. This could be the center of our horizon, say, at the time of recombination, will grow much faster than the size of the universe. Again, the size of the universe is given by this scale factor, okay, and the scale factor is growing very slowly. It's decelerating, therefore its amplitude is growing slowly. The size of the ball, therefore, is growing much more slowly than the size of the horizon. The size of the horizon is growing faster than that. As time, cosmic time. And eventually, those wavelengths, you can see here, which were outside the horizon, some will get in. And so on. More and more wavelengths are coming in. So the picture that we have is that inflation has been able to quantum fluctuations which were tiny, well within the horizon, to be stretched out to cosmological scales. So what we are observing on the CMB on our larger scales, it's actually nothing but quantum fluctuations that started out being very tiny, very small amplitude, well within the horizon. The usual quantum fluctuations that we observe in particle accelerators. So we're using inflation like a magnifying glass. We're using inflation to stretch out all those features of a space-time and fluctuations of the metric on a space-time, or curved space-time, to distances that are huge and that we can map and we can observe. It's extraordinary. It's doing the job for us. We wish we had something similar at much higher scales, because then we would be able to tap quantum gravity. Right. Not only do we have scalar metric fluctuations, there's also tensor fluctuations. I was describing those tensor fluctuations, they were the traceless, transverse traceless fluctuations that we associate with gravitational waves. So we can also write for those modes to second order an action. We can quantize that field. There will be, rather than just a single number, here we have two polarization tensors, the plus and the cross, polarizations of the gravitational wave, the symmetric transverse and traceless. These conditions tell me that there are certain properties between these polarization tensors, and the sum of these is just 4. Okay, the amplitude satisfies a linear differential equation, second order, which is very similar to that of the scalar. The only difference is that rather than z, this quantity which depends on the scalar field evolution, here only depends on the scalar factor. But that is also going to grow very fast. Right? In fact, it goes at 1 over e squared times the constant. Okay? So this can be integrated again, as we did before, with the same initial conditions which are deep within the horizon be Koskian, very large outside the horizon because of this equation where k is 0. Again, u v of k is proportional to a, with another constant, and we can work out the exact solution and the limiting factor. So, again, like before with the curvature fluctuations, since h of k becomes constant, remember this was v over a, the amplitude of the gravitational wave. When you go back, if you don't remember, here it is. H is the amplitude of the gravitational wave, it's v, this node, satisfy this equation, over the scalar factor. So this quantity becomes constant outside the horizon. So the gravitational wave, whatever the fluctuation well inside the horizon, has become constant. And the same behavior of the curvature fluctuation had for the scalar fluctuations here is valid also for the tensor fluctuations. So if they're constant, that means that we can again correlate what happens here to what happened deep inside the horizon, or as the fluctuation left the horizon during inflation. So these are the predictions that inflation does. Inflation will produce through quantum fluctuations features in the CMB, as well as in the larger structure, where those fluctuations grew to become the matter that we observe, galaxies, clusters of galaxies, superclusters of galaxies. But not only do we see through the photons this correlation of quantum fluctuations to metric fluctuations in the CMB, temperature isotropics, and from these to the structure we observe, but also there will be gravitational waves, which come all the way from inflation. So these gravitational waves we still have not detected. I'll use this lecture to mention some of our efforts to detect them. But if we ever do, the difference with respect to photons, if we ever measure, is that photons would tell us information about the last time those objects scattered off matter. The last time they did was at the last scattering surface, or if you want to have a combination. That means that when there was a plasma, before atoms form and the universe become neutral, those photons were very heavily scattered, just like photons inside a cloud. Therefore, we cannot tell, those photons have not traveled in straight lines beyond there, so we cannot tell anything of what happened behind it. It's, for us, the universe is opaque before. So the only information we can obtain from photons, because they're traveling unimpeded to us since then, is from the last scattering surface. So there's a natural horizon for us. We cannot go further. However, gravitational waves are so weakly interacting that the moment they are produced during inflation, all the way back 10 to the minus 35 seconds of the evolution of the universe, will travel since then to us without scattering. So if we have a picture of the gravitational wave background through the effect introduced in the CMB or direct detection nowadays we can talk about this in interferometers, laser interferometers, then we will have a picture of what was the universe like 10⁻35 seconds after the Big Bang. That's extraordinary. Okay, so I think there's tremendous potential in observations today, thanks again to this mapping of early to late universe. Right, so what are the basic inflationary predictions? On the geometry, on the very large scales, on the, if you want, zeroth order imperturbation theory, the background, and matter, we have four main predictions. First, homogeneity. The universe is homogeneous because it is acausal in origin. So fluctuations which were deep inside the origin have been stretched and came back in. That makes explanation of why the universe looks so homogeneous on very large scales. Then, the fact that the universe went through a tremendous expansion initially, which stretched all spatial sections, killed curvature, which goes by 1 over a squared, explains, or could in principle explain, the initial conditions that are required in order to observe today flat sections as we do observe. Moreover, not only are sections flat, in principle, given this tremendous expansion, even if there were an initial topological number, so even if the space-time was not sphere, right? It had handles, it had some topology, the topological cell corresponding to that universe must be at least 1,000 times what we observe. That is a very definite statement. It doesn't mean that there is no topology. It means that we are not measuring any topology today because of this tremendous expansion. It's possible, if inflation went on for many, many e-folds, that the topological cell will be so big that we will never be able to measure. Okay? So there is no appreciable topology of space nowadays. But moreover, something which I will go on next lecture on Thursday is all that tremendous energy density which drove the expansion of the universe eventually will end decaying from this inflaton into all the radiation and all the matter that is in the universe today. So that will give you the origin of the matter and radiation we observe. Something which, in the standard Big Bang theory, was something that had to be put in by hand. Here we'll see how strongly dependent of the dynamics of inflation is the reheating of the universe. So that's at zeroth order. What about first order perturbations? First, metric perturbations, even scalar or tensor, both, should be Gaussian. That comes about because quantum field theory on an essentially free field, both gravitons and the scalar field can act as free fields, behave like infinite momentum, infinite mode quantum mechanics, and each one of those modes is in the ground state. So the ground state of these Gaussian fields are Gaussians, and therefore this ground state will predict that the spectrum should be Gaussian. So if we do a statistics, we ask how probable it is to find a given amplitude in one place or another of the universe for a given wavelength, we see that these fluctuations satisfy Gaussian statistics. 3-point correlation functions are related to the 2-point correlation function. Moreover, not only are they Gaussian, they're also scaling variant, or very approximately scaling variant. And here is where we have some handle onto the actual dynamics during inflation, because the deviation from scaling variance is what characterizes the model. We're going to see the different models will have different dependency of the epsilon and the beta parameters, and they're going to give you different spectral indices. And this is the thing that we might use in order to correlate from what we observe on large scales today in the CMB, what is the dynamics of inflation. They're mostly adiabatic density fluctuations. That means if you have a single fluid, there is no chance that you might have two different populations which might exchange with energy and number, or entropy. Right? And therefore, if you have a single component, everything must be adiabatic. Photons, matter, barriers, etc., they're all correlated to each other. Because they come from the same origin. It's just a scalar field giving rise to matter and radiation. So that's another prediction, that fluctuations should be adiabatic. And there are specific signatures of non-adiabatic fluctuations which now are very strictly constrained by the same wave. Gravitational waves, it's a clear prediction of the theory. Their amplitude is proportional to the rate of expansion during inflation, and therefore finding gravitational waves from inflation will give us the scale of inflation, something which is still unknown. Okay? And there was some hope a couple of years ago of the possibility of having found such gravitational waves in the polarization of the CMB. Unfortunately, such a thing was not convincing. There were other sources, like dust in our galaxy, which got in the way. And nowadays, it's still not decided whether that is an actual gravitational wave, primordial fluctuation. And moreover, there are no vector perturbations. Vector perturbations arise in many models, among others in defect models of structure formation, which I won't go into in this lecture. But the prediction for inflation is that given that vector perturbations need to be sourced during inflation in order to be produced, and then later on re-enter, if you don't have a source, vector perturbations very quickly decay, 1 over the scale factor squared. And therefore, not producing them during inflation because they would require, they go in second order, the source is second order. If you don't produce them, then you don't see them also in the scene. And there are no evidences of vector perturbations. Cross correlations, for instance, between the linear or gradient polarization of the CMB and the temperature fluctuations. Okay, so how do we measure those things? Those are the predictions. How do we measure them? First, temperature anisotropies. We can use Planck, WMAP, and a whole array. And these are satellites. But there's a whole array of temperature fluctuation experiments on the ground. There are polarization anisotropies. Remember that photons from the CMB not only carry energy. Photons are vector fields, okay? So they carry vector polarization. This vector polarization could have certain properties. We can measure these two polarization states. And this vector polarization, as any vector, could be separated into two components, the gradient and the curl component, as any vector. The gradient component will be sourced by scalar fluctuation. You simply do the gradient of the scalar and produce something which is like an emo. Now, in the case of curl component, that cannot be sourced by the scalars. It could only be sourced by tensor components. So that is the reason why it has been searched for, this curl component polarization, so extensively, because it will be a clue to what is the amplitude of the tensor or gravitational wave contribution to inflation. For the moment, there is no evidence for such a component, Beagle component, famous Beagle component, apart from lensing. And it has been searched for by Planck, Weiser, and again, the whole array of ground experiments. That's for the CMB. Now, it's not, remember that we are observing nowadays scales that are entering or were entering the horizon since a few epochs, say redshift 300 or so. But also sensitive to scales that entered much before. Those scales, when they re-entered, they started to go through gravitational collapse and form structure. They are the places where those fluctuations would attract barriers. Barriers would fall in the potential wells left by inflation of those curvature fluctuations, and these potential wells will start creating stars, galaxies, clusters of galaxies. Therefore, if we could monitor, we could determine what is the cross correlation, the position, relative position between galaxies in our universe, all the way to redshift 1100, manage, then we would be able to connect the CMB anisotropies with the fluctuation during inflation with the magnitude distribution. And this is what large-scale structure surveys, was, so on, even before 2-degree field galactic survey. Nowadays, the dark energy survey, of which I'm a member, they're looking for the Barrow power spectrum, again, to make the connection with the CMB. Body acoustic oscillations, I won't have time to describe this in detail, it just simply means when fluctuations enter the horizon, barriers will fall in the potential wells. Obviously, they have photon interactions, that photon produces a pressure, the pressure restores the gravitational attraction, and they start acoustic oscillations. They start producing oscillations. These acoustic oscillations leave a mark in the CMB anisotropies that we're all very familiar with, but also leave an effect on the distribution of galaxies. It's a very tiny effect. It's for a few percent. But still, nowadays the resolution in the distribution of matter in galaxies is observed with sufficient precision that one can determine that we bump in curvature function. Okay? And then there's also weakness. The fact that there are distortions due to the presence of matter allows us to know where is the matter distributed, therefore what is the curvature. So we can ask here things like, is the distribution Gaussian? Is the distribution scaling variant? Okay. Is the power spectrum satisfies all the properties that were predicted during inflation? So we have new probes, not just the CMB. Okay, so let me go on then to discuss the CMB. What are those observations? And I will go faster here, since I noticed from your faces that you're very familiar with this. Okay, so I'm going to describe the density and gravitational power spectrum inflation model building. So what different models can we work out in this period that will give specific signatures in the after inflation. The prediction for inflation of CMB and LSS structure I mentioned very briefly, also very briefly on precision, and prepare things for the third mention, the reheating after inflation. Okay, we've discussed this. Fluctuations are stretched to cross-functional distances by inflation. They left the horizon and re-entered later. Now, remember that we could work out exact solutions for the scalar and the tensor components, but we can then ask, within this exact solutions, what is the two-point correlation function? And we can treat this two ways. We can treat these fluctuations as being a quantum mechanical fluctuation that outside the horizon became classical, through what I don't think I'll have enough time to describe, which is a property of classical transition as the fluctuation crosses the horizon, or treat it as a quantum mechanical problem. What is the two-point correlation function in momentum space between the vacuum? Okay? Both ways, you get exactly the same answer. It's a free field, and therefore the quantum mechanical description of a Gaussian free field is actually equivalent to a statistical description of a Gaussian random field. Okay, so one-to-one correspondence. And this is well known for many people, for a long time. So if we do this two-point correlation function, we can describe the phase in terms of the power spectrum, defined this way. The correlation function is the power spectrum over 4 pi k cubed. This is, if you want, the power spectrum per logarithmic interval in wave number. Okay? It's a two-point correlation function, which is a delta to k and k prime. That means modes are uncorrelated. Okay? And the amplitude is proportional to the ratio of UK over Z. Remember that was constant. Okay? And depending on some spectral index, which itself depends on the slower parameters. So we can write this power spectrum as an amplitude times a wave number to some power. That's all you need, two numbers. An amplitude and a spectral index. In general, the fluctuation will have some curvature. Okay, it's not just simply exact, because the rate of expansion is not exact. It's not just constant. Therefore, there will be variations on the scale of x. You're running of the spectral index, that's what it's called. So we can ask then, with the fluctuation rate at the horizon, what is the amplitude and what is the tilt? So the amplitude is proportional to the rate of expansion, but it's inversely proportional to this lower parameter. And this tells you how slowly the scalar field evolves in its potential. If you have a very, very flat potential, it will be extremely small. So in order to get an amplitude, which is 1 part 10 to the 5 squared 10 to the minus 10, you need rates of expansion small, if this is a small one, or large, if this is large. Okay? So from this CMB, we cannot yet determine what is the rate of expansion during inflation, because we always have this uncertainty. We might infer from the spectral index, as I'll describe in a minute, what is this relation, but we still have an uncertainty. We don't know what is the curvature of the fluctuation, of the potential. So what is the deviation from 1 of scaling variance? It's clear that if you have a scaling variance spectrum, as I was advocating, NS is very close to 1. This is just a matter of historical notation. Hartons and Zelnovich in the 70s, early 70s, realized that the matter distribution could be described if metric fluctuations enter the horizon or were set up on very large scales to be constant with a spectral index of 1. This is what accounted for the way galaxies were distributed on large scales. So they say, okay, the most natural initial condition was a scale invariant initial condition for the metric fluctuation. They obviously did not have in mind inflation. So inflation did not predict this. The idea of inflation initially, when it was proposed by Alan Booth in 1980, was simply trying to solve the basic problems, the shortcomings of the hot Big Bang. They have no idea that such a scenario would give rise to fluctuation, which exactly were predicted much earlier by Huggins and Roach. It's a prediction of the model, which fortunately was confirmed by observations. Now, the reason why this spectral index is so close to 1 is because during inflation, these two quantities are tiny, of the order of a few percent. That's why we measure today NS to be 1 within 4%. Okay? So it's quite interesting that indeed there are many models that predict that these quantities are small. But which one of them is still under question? We don't know. Not only do we have the tilt, we can also work out the running of the tilt, and this incorporates another quantity, the third derivative of the potential. So by adding more and more derivatives of the potential, we can go higher and higher in the order of running of a spectral index. Not only do we have an amplitude and a tilt, the running, and the running of the running, etc. Okay? So. Right. So I was describing, not only do we have density fluctuations, which are density waves in the way curvature is mapped on space-time hypersurfaces, but also you will have gravitational waves. These gravitational waves are transverse and traceless. They're very different from the density waves. These can be observed and have been observed in the CMB. These have not yet been observed. But fortunately, this picture, by the way, is very different from this one because it's in ordinary time. We have to stretch this to perform a time, and then, in terms of the scale factor, to be able to see such a map as I was describing in the first lecture. Now, this is what I wanted to get at. So we have the scalar and tensor fluctuations. Both have similar amplitude and tilt dependencies. If NS is 1, this is exactly scaling invariant. If it's smaller than 1, it's not quite. It's called the red spectrum. It's larger and smaller scales, the red part of the spectrum. If there is a variation of the spectral index with time, then DNS and spectral K, the running being smaller than 0. Here it is. There is, fortunately, a relation between those two. Imagine that you did not know what was the origin of fluctuations, and you did not have a model of inflation. Then, that would correlate those two. Then, the amplitude of fluctuations in the metric, the scalar fluctuation, and the amplitude of the tensor fluctuation would be completely uncorrelated. There would be no reason to argue for any connection between tensor gravitational waves, which could have been produced from very violent phenomena, the origin of the universe, and the fluctuations which give rise to anisotropes in the same. No reason whatsoever. However, inflation, as I was describing yesterday, has something quite strong, and that is very robust. This is this low-roll attractor. That means that whatever my dynamics, I start in any point in phase space, I will end up at an attractor. That means that there's a single function, v of phi, determining the whole evolution of the universe. That single function, v of phi, is the only thing I need in order to map not just the growth of the background, but also the fluctuations that you can see into the background. Okay? So inflation gave away with any fluctuation that was prior to it, so got rid of all the fluctuations, but it printed its own fluctuations. That means that there must be correlations. If you have a single function giving rise to two power spectra, the power spectrum of scalar fluctuation, the power spectrum of tensor fluctuation, there must be necessarily a connection between the two. It's a functional connection, it's true, but if you simplify things, as we can do here, with amplitudes and tilts, then necessarily there must be, given that there are four quantities, two amplitudes and two tilts, there must be a relation between those four quantities. And in fact, there is such a relation, it's called the consistency relation. For single field adiabatic fluctuations, the ratio of the amplitude of the tensor spectrum, which was proportional to the rate of expansion, over the amplitude of the scalar spectrum, which was proportional to the rate of expansion over epsilon, must necessarily be related to the spectral index of the gravitational waves. Unfortunately, this is not the spectral index of the scalar fluctuations, because we still have the curvature. Otherwise, we would immediately predict what the amplitude of the tensor spectrum is, and then go and measure. So it's only depending on the epsilon factor, and therefore you still have an uncertainty. So we still do not know what the rate of expansion is. So this is a quantity, famous R quantity, which is the holy grail for CMB and LSS for the next generation of experiments. It's the thing that people are searching for. At the moment, it is bounded by Planck to be less than about 0.07 or so, at 2 sigma. In the future, we might reach R for a few per million, with LIGHTBIRD, with CORE, with whatever large satellite will come in. Okay? So we are in for a tremendous revolution in observations with thousands of detectors that will be able to go down in this parameter R to the few per million. Many of the models, I will show you in a minute through what we build, many of those models will be ruled out if we're not found of inequilibrium observations. Okay, so let's see what are those models. Okay, up to the moment, I've just talked in a very generic way of inflation and that is driven by a scalar, an effective scalar, with some dynamics. I didn't go into what the dynamics were. Okay. There's a whole array of possibilities. You could have effective descriptions of a gravity phenomenon, for instance, in Starobinsky model, where we were seeing yesterday from Jose, the scalar curvature is not just the only action that you can write with Hilbert action for gravity. You could ask the generic function of R, f of R. In those models, there is an extra degree of freedom, which is a scalar. It was found by Starobinsky. It's called the scalar. The scalar here could act like inflation. It has a potential which is approximately constant in the frame that I'm used to here with V of phi. And this constancy of the potential is enough to drive inflation. So even in high order theories of gravity, it is possible to describe the model of inflation without any connection to particle physics at all, only gravity. Of course, since we're talking about fluctuation which probably have to do with high-energy physics, much beyond the standard model, much beyond the electroweak scale, possibly, and it's still unknown, at the scale of the gradient so 10 to 15, 10 to 16 GeV, it is possible that new dynamics there, which we're completely unaware of, might give rise to the fluctuation that we observe in the same. So it's open arena. We don't know what the model of inflation is. So people have classified this model. Some people talk about single field, large field inflation. So we start high up models which are monomials with high powers for etc. Or even n squared phi squared. Or exponential. This would be large field. The reason why the scalar field is evolving slowly, having this tremendous slope, is because not only V of phi is large, also the rate of expansion is large. And remember, rate of expansion is a friction force in the evolution equation for the scalar field. And therefore, it's slowing down the evolution. The higher the scalar field, the larger the rate of expansion, the slower the scalar field evolves. Okay? So that drives inflation also. Moreover, you could have a small field inflation, something like this, it's called a top inflation. So you could have inflation starting at some symmetric point, and then slowly evolving away from it. Here, again, this is essentially vacuum energy, so you're at the top of the potential, your energy density is essentially constant, and as you move away, your energy density decreases and eventually you get inflation as you go to the minimum, for instance, of this potential. Or you could have something in between. So you can have hybrid models where you start at large values, but then you end up on a constant energy density. So this would go like constant plus some extra potential. These kind of models, they give rise to spectral indices which are bigger than 1, but there are other models, hybrid, moving away from there, which would give you the proper rate tilted spectrum. Okay? So all these models can be classified in the plane of spectral indices and ratio tensor to scalar in this way. They're more or less, of course, there are boundaries. For instance, hybrid models can have n smaller than 1, which is no problem. Large field models have these ranges, or typically 4 ranges. So, how do we deal with this? So, we take out from our hat, or from our pocket, a given potential. And we ask, what is the value of the slower parameters, epsilon and eta? What are the number of e-folds from a given point in this model down to the end of inflation. We compute the amplitude and tilt of the scalar and the tensor spectrum, and possibly the running. And then we ask, what is the prediction that this model has for the CMB isotropies or the logical structure power spectrum? So let's think of a single one which is very easy to deal with and in fact has an exact solution. Let's suppose that we have a potential of this type, one of these large fluid models. Okay? So we assume that the universe started with a potential which is exponentially growing, so it goes like d to the minus beta kappa, and then this field is slowly evolving, okay? And it's going towards actually to infinity. There is it. Now, remember, the evolution of this model can be worked out exactly using the Hamilton-Jacobi equation, without any slow-roll approximation. There is an exact solution to this, which is beta h proportional to phi dot, which gives you a rate expansion, a single function now, which is a combination of v and its derivative, which goes like this. Minus 1/2 beta kappa, where h naught, this constant quantity in front of the exponential, is constant. Okay? So, this drives inflation. And we can work out all the parameters, epsilon, delta, psi, etc., and they're all constant. So remember, before we were assuming that this parameter was sufficiently small that to second order, their derivatives would be constant. Sorry, it would be zero. Okay? Their derivatives would be zero because they are proportional to epsilon squared, which is much smaller than 1. But here, they are exactly constant. This is called power law inflation. They're exactly constant, and you can work out what are these coefficients, you can work out what is the spectral index, exactly. You can work out what is the tensor to scalar ratio, and if we put in the number that we measure from Planck for the spectral index, 0.964 or 0.967, if you can third digit, and I just got rid of it, ignored it, 0.96, then we have a specific prediction for the power p. And if you want, for beta and p are related. Okay? That means that p is large, beta is small, fine. Then that means that epsilon delta plus 1. Okay? Indeed, it's consistent. Among other things, the fact that NS is constant means that there is no running. For this model, there is no running. Most other models do have running. But what kills the model is the fact that since there is just a single number, p, characterizing all of the fluctuations, we can't see whether it satisfies also the tensor constraint. And it does not. If we work out, substitute here the value of p, we work out that n, the tensor index, is exactly equal to the scalar index minus 1. So the reason why the scalar fluctuation is scalar invariant is the same reason why the tensor, the spectrum is scalar invariant. In this particular model, not in other model. But you can then work out what is the ratio of the tensor to scalar. We find a number which is significantly above any sigma what is measured by the CMB and LSS, for instance. So this model is ruled out. One of the first models to be ruled out. You can work out another model, n squared phi squared, chaotic inflation. You go through the same analysis. You substitute here the present value. And you see that it's, okay, it's perfectly in agreement with observations, surprisingly, okay. But it has a tensor to scalar ratio, which, how should I say, it's ruled out. This is a more transparency. 0.13, which is already ruled out. You want to see. Starobinsky inflation, what I mentioned briefly, okay. Here, it comes actually from quantum field theory, its origin, comes from quantum field theory in space. You could go to effective action formulas and write this as an f of r theory, like Prof described yesterday. Make a conformal transformation and go from g to g tilde with a prefactor, which depends on the single field, phi. This will be the scalar, and the potential for the scalar can be worked out exactly. It has this shape. So asymptotically, when phi is very large, this goes to 0, it's constant. It has this shape. For the moment, this model is perfectly in agreement with observations. These fluctuations will move along this flat plateau until they end inflation. So we can compute here what are the epsilon and beta parameters, and from there determine NS. All the four components. And for the moment, this is perfectly in agreement. Just like chaotic inflation has a prediction which is very close to what is observed, but different with respect to n squared phi squared, it is not ruled out. You have R, which is 3 k to minus 3. So here is the plethora of models. Starobinsky inflation, chaotic inflation, high inflation. You could have many different scenarios. It's clear that the dynamics are completely different from each other. It's still, the amplitude that we observe in the CMB is the same for all of these. It's the tensor contribution which might vary from one to the other. We've seen this. So how do we measure this? Through this temperature fluctuations. Maybe we could stop here if you want. Is that okay? We stop here for 5 minutes and then we come back because I'm going to change gears totally. I'm going to go from theory to observations. Okay? Is that okay? So are there any questions before we go for a break? Yes?
Yes, from the drawing on the board, it's like...
Speak up.
From the drawing on the board, it looks like if I start the field up in a different place, I get power law or something that wouldn't there.
That's too steep. In principle, that's okay. The potential so of the sword. Let's say kappa squared. So when you go to -5, okay, this is very fastly growing because alpha is not small. Remember that in a power law inflation, which would be of the type exponentially decreasing, if you go to the other way, you needed beta, which was extremely small. Beta was 1 over 2 t squared, t was 450. Okay, that means that beta would have to be extremely small. While here, alpha, we know exactly it's 2/3. So that's so too big to produce inflation. It's so steep that it would never produce inflation. The only way in this model, the only place in field space to produce inflation is through this attraction.
So you said the slower always an attractor, but you really do need a specific field value. You need to start the field.
That's right. Normally the attractor is such that in field space, you start from whatever motion very quickly fall into the attraction. But
so whatever derivative is fine, but the actual field value is important.
The field values cannot be anywhere. Yeah. There is a basing of attraction. Okay? So if you're beyond basing of attraction, it would take quite a bit of time until you reach the attractor. And therefore, if those are the last EFOs, you will not be in agreement with observations. You have to go through the attractor and those fluctuations be sufficiently well within this overall approximation and with an amplitude which is in agreement with observation. And that's not automatic. It's very much abnormal. Okay? The issue of what were the initial conditions for those field values and their derivatives, it's a whole issue. It is related to the measure problem in quantum field theory. So we don't quite know how to evaluate the probabilities of finding yourself from, say, quantum gravity standpoint at a given place where a given value of phi and phi dot. Okay? So there are some arguments that some of these models could be fine-tuned in their initial conditions. So there has been in the literature quite a discussion of how difficult it is. It's true that inflation is an attractor. Once you start expanding very quickly, you will go through the phase that you're looking for. But how do you get into that phase? Okay, it's an issue that has been in the literature. Now, there are, as I said, very subtle issues. If you take into account quantum fluctuations, so if you go into the stochastic inflation scenario or formalism, then you realize that it's not just what is phi and phi dot, it's what's the amplitude of the rate of expansion. Because that's going to give you quantum fluctuations at that stage. Those quantum fluctuations may be much stronger than the drift force that takes you down through this low rumble. So you might start up, let's suppose we have, I won't go into stochastic inflation within these lectures, but let me describe very briefly. If you're at sufficiently large values, this is called the self-refraction regime. At certain values, remember that delta delta phi is proportional to h, which itself is phi. But delta phi, which is phi dot, then delta t is p prime over h. Okay? So, these are both phi dependent fields. If you're sufficiently large values of phi, then these fluctuations are much faster than these ones. So the drift, which takes you to the bottom of the potential, cannot be compensated by the quantum fluctuations which drive you both ways. Okay? It's a random process. So there are certain patches of the universe where those fluctuations gain over the drift, and therefore you move up the potential. Rather than going down slowly with little fluctuations, giving rise to different metric fluctuation, different types of the end of inflation, some will go up. And since they have larger rate of expansion, they occupy larger volumes. So the question is, what is the probability of finding yourself in a given patch, and where this patch gave rise to one universe like ours after the end of the whole evolution? And that's something which, again, it's really a measure problem, and it's very difficult to evaluate. There is not yet any reparameterization invariant way of characterizing the probability measure. It's a whole issue nowadays. I'll describe those probabilities. Any other question? Yes?
Going back to initial conditions, you said inflation gives you flatness, right?
Yeah.
But then you started off with the assumption of a perturbed freedom of Walker, and then quantize that. Is that a valid assumption to make?
Right, that's a very good question. It has to do again with the initial conditions of any patch of space-time. So in principle, one should do some kind of path integral quantization of a space-time, will do it, and then ask yourself, what is the probability that a given patch will appear of a space-time with a given property, curvature, fluctuations being one of those, right? So in principle, it's very difficult to classify all possible metrics, and then go through the measure problem and finding the path integral, what is the probability of finding yourself through such an evolution. So normally, the thing you do is the most obvious one. You go to Bellido superspace, look for the most simple description in terms of a Freeman-Walker universe with some curvature, and ask what is the measure, what's the probability of finding such a universe with some curvature in your distribution function. And the measure seems to support that the fluctuation, if you start from nothing, an identical wave function, then you will end up with a universe which is homogeneous from start. So the probability of jumping to a unit which is very inhomogeneous is less probable than that jumping to a homogeneous patch.
That would seem to be counter to the idea that entropy is more likely. And then highly entropic states are more likely. Sorry.
But that's the solution of the Bellido wave function from turning from nothing.
Yeah.
It's an issue still. Where these fluctuations, where these patches which came out of quantum fluctuations of space-time ended up. That's the issue. So we're assuming that somehow quantum fluctuation of space-time, as described yesterday, will give rise to a patch which starts growing exponentially, and then afterwards enters into this local regime, and since then goes through all the phases that I was describing. So in this picture, those questions have to do with that limit, of which we still have great uncertainty. Of course, they would be related to the extremely large structure of the universe at scales much bigger than the present horizon or observable universe. So they're not amenable to observation. At most, what you would do, if we ever solve the probability or measure problem, you might ask, what are the cross-correlation properties in our patch that come from the fact that they arise from a given probability distribution, a unique probability distribution. So if we ever solve that problem and are sure to evaluate those probabilities, it will be the conditional probabilities of observables within a given element of the distribution. Our universe will be a single element. Properties within that element might tell you about the overall distribution. But that's very far-fetched. We were thinking of these in the 90s, the unrated stories, stochastic inflation. Any other question? Yes?
You mentioned that the spectrum of the fluctuations is Gaussian because of the ground state of the quantum state.
Right.
I want to know how does that relate to non-Gaussianity when people look for other models?
Good question. The non-Gaussianity that we might observe eventually in the CMB on smaller scales or in larger structure, looking at the endpoint correlation functions, 3-point at least, might have different origins. They could come due to the fact that when 65 defaults occurred, the fluctuation were not yet in their ground state. For instance, it might happen that our potential has a bump. We use the board. Imagine that you have a potential of this sort. So your field gets stuck for a while here, then suddenly tunnels through. Okay? So when it tunnels, it produces a bubble. Within the bubble, you still have energy density. And therefore, your bubble is full of energy. Your bubble has bubble walls. Those bubble walls can be used to define the metric, which is that of an open universe. And this open universe, as it has energy inside, it starts expanding. Okay? So the outside universe is the cylinder, because you're stuck here. But the bubble inside has energy and it's an open universe. Soon that open universe starts becoming more and more flat, because there will be some default from here until the end of inflation, and the field evolves and produces all those fluctuations, where the expansion is stretching the fluctuations. Okay? However, if the number of defaults from this moment to the end is exactly 65, you still have properties that are sensible to what was this instant that took you across the bubble wall, took you across to this barrier. So those fluctuations will not be in their ground state. On the contrary, there will be bubble wall fluctuations. We worked this out in the 90s or so. There will be bubble wall fluctuations which are modifying your spectrum. Okay, there will be extra fluctuations. That means that your nodes are no longer in the vacuum, so there will be excited states of your metric fluctuations. Those excited states will give you non-Gaussianities. Okay, that's one way of producing non-Gaussianities. Another way is, nothing to do with this, you have other fields. So it could be that your scalar field is not alone, it's not a single field. There are multiple fields, and those fields have couplings with the inflaton in such a way that if those are strong couplings, then part of the energy goes into those other fields. Those fields are also fluctuating during inflation. And these mixed fluctuations of those two fields induce correlations. You cannot treat these really as a fully decoupled system. So both of them are strongly interacting. And therefore, again, you're not in the ground state for any of these single fields. And you have scattering issues. So at the level of the fluctuations, those fluctuations will talk to each other. And this induces KK prime length coupling, and this induces non-Gaussianities. Very similar to what happens when fluctuations re-enter the horizon and you go through gravitational collapse. There's also coupling. There's also connection between different wave numbers which induce non-Gaussianities. Furthermore, there's another way in which if the dynamics, as also was described yesterday, dynamics is complicated for the scalar field. It's not just a kinetic, canonically normalized field with a potential, but it's something like a much more complicated kinetic structure or a Hornetsky type, very complicated scalar to gravity couplings. Then, again, the fluctuations are no longer Gaussian. Then you will have non-Gaussianities induced by the fact that those kinetic terms are non-canonical. For instance, there could be a speed of sound for the fluctuations. It's not exactly the speed of light. It has a value which is smaller, and then you will see differences in the ratio of tensor to scalar. You will see non-Gaussianities, it's called the FN. I won't go into this, this is not the level of this course. So there are a whole plethora of different phenomena that could give rise to non-Gaussianities. For the moment, CMB observations, as I will describe in a minute, do not show any non-Gaussianities. But that's only very restricted because we only observe going smaller scales, where these non-Gaussians could arise. Okay? There might be non-Gaussian features at much smaller scales, which are still not under probe. We can't. So the whole purpose will be, in the next decade or so, will be to search for phenomena in our universe today, in our present universe, that will be able to correlate through this complex of geodesics back to dynamics during inflation. The more we know about what are the predictions here, the more we will know about the other universe dynamics. So it would be great if we found non-Gaussian features which were not due to gravitational collapse. The problem with those small scales, you can answer from what I was just saying, is that gravitational collapse mixes modes, and therefore things that happen in the late universe could mask what was actually going on. Okay? So when gravitational collapse produces a non-linear growth of fluctuations, it will mix modes. And this mixing of modes will mimic the non-Gaussian feature. So one has to deconvolve the gravitational collapse to get back your primordial. This is something which cannot be done. It's an inverse problem. It cannot be done in a linear way. You have to do full nonlinear, and therefore it's quite difficult. And it's from quantum optics. It's extremely difficult to infer what the emission spectra. So typically you do simulations, and of course they are prone to have certain assumptions built into them. So it's quite difficult to get back the primordial spectrum. It's possible that you might have some remnant of such a gravitational collapse, which is mimicking the primordial non-Gaussian feature. So we're very careful. People like me, members of large-scale structure collaborations like the Dark Energy Survey, we're very careful of being able to subtract such non-Gaussian features from gravitational collapse, and do not claim we found a non-Gaussian for two elements. Similar to what happened, as you will see, with bisectors. More questions?
You
yes.
mentioned that the gravitational wave has two polarizations.
Yes.
So what is the difference between this polarization and the normal polarization of
I wrote your last question. What is the difference between these polarizations and?
the normal polarization of electromagnetic.
Okay. Gravitational waves and electromagnetic waves are very different in the sense that gravitational waves are tensorial fluctuations, okay? Therefore, they're not acting like vector fluctuations, which is how the electron oscillates back and forth, which is like a vector, okay? And you can determine the linear polarization of an electromagnetic wave, but just simply determining its position, its vector, okay? It's transverse, so you have your electric and your magnetic field, and you can determine the polarization by putting in one integer, very simple, like we do precisely for the CMB, okay? Now, in the case of gravitational waves, it's different. What gravitational waves do is produce shear. So imagine that you have a circle of particles, and a gravitational wave goes across. What it would do is push this circle into an ellipse, and then it would do this. This is the way matter evolves under a gravitational wave as it goes across. Okay? It's very different from a charge, which just simply would do this back and forth motion, which is a vector. This is a tensor, it's shear. Okay? So it's decreasing and increasing, decreasing and increasing. So there are two ways you can increase and decrease. Plus, like this, or like this, cross. Those two polarizations are linearly independent. Okay? So the same as we can draw a vertical line this way and this way, those are linearly independent for the vector polarizations of photons. You can write for tensors also two modes. They're radically different in the way they act on matter. One acts on charges, the other one acts on any kind of matter. So when we measure the CMB anisotropies, we will have a combination, actually, of both polarizations. We're not going to be able to disentangle them. We do predict from inflation that certain type of circular polarization cannot be produced. This is true. Because of the way the polarization, the tensor component was produced from inflation. Okay? So this is a specific prediction. For the moment, the only thing that these experiments are going to measure is their amplitude. They're not going to measure the polarization. You're adding them incoherently. You cannot determine. It is possible in the future, with laser interferometers, the fact that you have different arm lengths and you have different detectors at different positions on orientations on Earth. Okay, one in India, the other one in the United States, the other one in Italy, etc., or in Japan, the different orientations might help us determine the polarization of the gravitational waves. So if we measure a stochastic spectrum of gravitational waves from inflation with a detector like this, we would be able to know what were the polarization components of the gravitational waves. Otherwise, from the CMB, it's very hard. We don't have enough resolution to tell apart. More questions? Okay, let's go then. Continue. Right, so we have, as I was saying, fluctuations imprinted on space-time from inflation, which re-enter back in and perturb space-time this way. Imagine that you have the last scattering surface. So before scattering, you have a plasma. The universe is too hot to maintain atoms. So they ionize the atoms. Those photons are very active. There are plenty of them, 10 to the 10 for each baryon, essentially. And therefore, they're enough to ionize the plasma. So that plasma is living on a space-time which is not flat. Space-time is curved because of these fluctuations. It's true that it's a very tiny fluctuation, 1.10⁵ in amplitude. But still, it's enough to change the pattern of a scattering of photons of the plasma. The moment those photons scatter off for their last time, for instance, think of this one, scatter off an electron and left the last scattering surface, and didn't scatter again. Why didn't they scatter? They didn't scatter because the universe, at this time, become cold enough that photons no longer had enough energy. Remember what happened with photons? Their energy density also decreases. It's also redshifted, the famous redshift. So their energy is not enough to ionize this atom, and therefore the atoms conform. And they become neutral. Once the atoms become neutral, there are no scattering centers for photons. So the last scattering will occur on a surface. It's actually not quite a two-dimensional surface. It has some thickness, because the probability of scattering is not abruptly changing from fully ionized to completely neutral. Okay? This transition means that there is a width to the last scattering surface. Okay? So there will be a moment where those photons last scatter and then they left. Okay? And we'll see that this last scattering will determine the polarization of the CMB as well as the energy of the photon that last scattered. Right. Now, these photons, when they scatter, there are three components to their frequency. One is gravity. We are all very familiar with the fact, redshift, blue shift, that if photons come out of a deep potential well, they lose energy as they come out of the potential well, the famous redshift. Okay? Or they gain energy if they fall into the potential well before the last scattering. So we're going to see on the last scattering surface, places where you have larger and smaller potential wells will have different colors, slightly different, one place to the other. It will be redshifted or blue shifted, depending on where did that photon come from. Where it's the potential well induced from inflation and entering the horizon, which determined what was the frequency of the photon on the last scattering. There's also, since we are in a very tightly coupled plasma, photon baryon in equilibrium through quantum scattering, these are relatively weak photon baryon interactions, through electromagnetic interactions, okay? Then the motion of baryons are also going to determine the frequency of the photons. Baryons moving towards potential wells, trying to concentrate into the deep potential wells, they will gain velocity. Okay? In their phases, they're falling towards the potential wells, they have a velocity. When a photon is scattered off of the moving baryon, it will get induced a Doppler effect. Okay? So it's going to change its frequency. Just once it reaches us from the gravitational wave. And finally, there's a density contribution. This is the fact that in those deep potential wells, you have much more concentration of baryons. Those baryons are interacting with the photons and adiabatic fluid, and therefore any fluctuation in baryon is going to be reflected in the fluctuation in the temperature. These three components, gravity, velocity, and density, allow, and they contribute to the CMB absorption. And they contribute the way I will show. Remember the basic fact: fluctuations during inflation come out of the horizon and re-enter. Okay? So imagine that you are at a given time, which is last scattering surface, and this defines a scale. Right? Last scattering surface has a given size, okay, corresponds to the time it took a photon from the beginning of the universe until the last scattering time, 380,000 years after the Big Bang. Okay, that's maximum size of the Big Bang. Okay. Now we can ask what was the wavelength of the fluctuation compared to this size. It's going to be a reference frame, the size of the horizon at last scattering. So fluctuations that have wavelengths much smaller than the horizon entered earlier. Remember, let me go back here. Fluctuations that have wavelengths smaller than the horizon came out later, they expanded and entered earlier. This is the time they entered the horizon. Okay? Before last scattering. This will be last scattering. This is before. And therefore, once they have entered, they will feel the potential waves. Okay? Those barriers which were there feel the gravitational attraction of the curvature fluctuation. They go to the potential wave. They will try to concentrate their scan of photons. They will feel the restoring force from radiation pressure. The radiation pressure will tend to dilute the gas. Gravitational attraction will attract them again, dilute, attract, dilute. Compression will form. So you will have an acoustic wave. The acoustic wave will be seen, I'll show you in a minute, in the CMB. Now, there are wavelengths which are much, much bigger than the horizon at that time. Those are wavelengths that entered much later into the horizon. These correspond to these wavelengths. Okay? At the time of decoupling, they were way out of the horizon. Okay? These wavelengths, barriers that live on that space-time, on very large distance from each other, don't see each other, do not feel any gradient. So they're not moving. They're essentially constant. Okay? Those barriers are not feeling anything but the gravitational potential. They're not feeling the density or velocity component. Okay? But there is a wavelength, a characteristic wavelength, which is that for which the perturbation exactly has the same wavelength as that of the size of the horizon at decoupling. For those wavelengths, these barriers are beginning to move. This is the moment in which they go through first compression. They're starting to move towards compression. So let's put all of these together. Let's have a diagram where here we have redshift, here we have angle. The small angles correspond to smaller wavelengths. Angles projected in the sky correspond to smaller wavelengths. Those small wavelengths actually entered earlier in the horizon, so they started to collapse earlier. They went through maximum compression, later on through rarefaction, maximum rarefaction, and again started to fall in. Wavelengths that entered later, so the redshift, are much bigger than these ones. They are larger angles. I put it here in this. Okay? Small angles, large. These started falling in much later. They went through compression, started to come out rarefaction. These started earlier, much bigger wavelength. Again, same phase. Remember, something which is crucial and does not happen for any other fluctuation is that here the fluctuations have a clock. Fluctuations, remember, were constant in amplitude outside the horizon. When these fluctuations enter the horizon, they start filling the causal evolution induced by the presence of that matter within curvature. And these start to fall into potential waves. So they have a clock with them. The moment their wavelength is of the order of the size of the horizon, when they enter, they start moving. Until then, they're completely static. Okay? Once they start moving, they go through compression. And that determines the phase at which they enter. Exactly tell you what happened, whatever the position in the sky. It doesn't really matter. The only thing that determined that fluctuation started its phase to start compression was their wavelength. So even if that region and that region, which are causally disconnected at the time of the coupling, the fact that it's their wavelength which determines their clock makes that these will go in phase, even if there is no correlation. There is no line that will tell them go in phase. There's no microphysics telling them. It was the early universe which determined their wavelength, which is going to give them the phase. And they're all in phase. This is so extraordinary. This is the thing which makes the CMB and LSS so unusual. That those fluctuations, when they enter, they have their own clock, whatever the position is, even in possibly disconnected matches. And it's this clock which determines their phase of oscillation. So wavelengths which enter much later, then go through compression. Those that just entered at last scattering, this is, remember last scattering surface had some width. Okay? Those that just entered mass scattering went through the growth. And those that did not even enter, so they were still outside, were constant. So if we take this series of compression, rarefaction waves, and so on, and we square them, then we do that without the mathematics first. Yes, here it is. Those fluctuations on very small scales would have gone through a series of compression rarefactions. And what we observe in the CMB is like, from here, it's like a snapshot. So we're making a photograph of those fluctuations. Well, when we observe the CMB, and we look at all scales, we're asking, when did I get these photons in their motion? I'm going to make a photograph. Scattering occur, photons no longer scatter, the probability is less than 1 part in 10 to the 3, and therefore their phase, what is their amplitude at that stage, will remain equal until it gets lost. Okay? It has not been perturbed because there is no further scattering. Therefore, what we're observing when we make the photographs is we got those photons, and therefore the density fluctuation from the baryons, in place at the time. So we're going to see what was the phase of compression and rarefaction of each one of those photons. So the reason why we can observe these happening, so that there are peaks in the spectrum of two-point correlation function as a function of angle, or here in multiple numbers, is because all those nodes at very different locations have exactly the same compression and rarefaction. They add up. There's coherent enhancement of the fluctuations. It would not have happened if that patch and that patch would be actually totally uncorrelated, because they would be in different phases. And you would never add up compression and rarefaction. You would end up having compression and rarefaction in different positions. These would essentially give a bump in the power spectrum. Now, what is this power spectrum? This power spectrum can be computed. We're going to have a formula. Is it here? You can compute the temperature fluctuation as a function of angle on the CMB. This is proportional to the curvature fluctuation. And you can expand it in multiples with spherical harmonics. Compute the CL, which is nothing but the square of these coefficients, which, on the other hand, you can write also as a two-point correlation function in angle. So how probable it is to find a given fluctuation in that direction, this direction, as a function of the angle between the two directions. Okay? Right here. It can be expanded in the Genter polynomial, which are combinations of the spherical harmonic, with coefficients which are the CLs, the square of this. CLs, fortunately, can be written in terms of the primordial spectrum. Here we go. So we have two-point correlation function, remember, was related to the power spectrum and the scalar fluctuations. Why? Because this two-point correlation function, which depends on the amplitude of the metric fluctuation itself, remember this relation between the curvature fluctuation and the metric fluctuation relates to the power spectrum. Therefore, I have a prediction for what is those coefficients of the two-point correlation function expansion of the angular correlation. It's called the power spectrum, angular power spectrum. So if we do this integral for an amplitude and a tilt, which is constant, then there's an exact expression. For n very close to 1, which is what we measure, we get that CL L plus 1 is approximately constant. And this is the reason why all the features that you see, oh, sorry. Here, are drawn in an amplitude of the CLs times L plus 1. So this flat plateau, what's called the Sass-Wolf plateau, is related to the fact that on very large scales, only the gravity contributes, and this gives essentially constant value for L plus 1 scale. On very small scales, as I said, first we have the compression right at the time of the last scattering at angular separation of about 0.8 degrees. And smaller scales we have higher peaks. Okay, so going beyond the computations, here are the predictions for the temperature power spectrum of the scalar component. The temperature tensor spectrum, which is very quickly, once you go inside the horizon, gravitational waves, and any other photons, and any other fluid, which is characteristic, will very quickly redshift away, its amplitude decreases very fast. The square of its amplitude gives the power, and therefore the result inside the horizon, even if we have fluctuation, will very quickly drop. So the temperature contribution drops dramatically. The polarization will have a component, which is the gradient component polarization, which has a bump at recombination. And here are different values of the BB cross correlation, the curl component of polarization, for different values of the tensor to scale ratio. Obviously, if the amplitude of the tensor contribution is tiny, because the scale of inflation is tiny, then you're not going to see the effect. Okay? You'll be well below the noise level, and that's what happened with passing. I think, what time is it? Have we got a few minutes? No. Then we shall stop.
Okay, cool.
Thank you very much.
Thank you.
I will continue.